Yeah, yeah, right. Right. You're so very welcome. So we started going through material codes. How the end of the semester is going to handle is I'm going to get as far as I can today. Okay. I didn't post any more notes, but I went through and I developed a bunch more. I'm going through some very modeling specific elements. Like we kind of briefly talked about it on Friday about doing like, okay, how do you get, in our case, like the homework is, you have this member and now you're intersecting that member with a plate and that member has stiffness or, to it, and it's not gonna just be connected at one discrete, like finite point, right? It's gonna be like a column in a foundation or a column that's landing on a base plate in your homework, right? So you gotta come up with ways to do that. So I'm gonna talk a little bit about foundations, slabs on grade, and there's a few other elements. I wanted to talk to you about like retaining walls, underground tanks, stairs and floor systems. So for those of you that were that watched Matthew's presentation in steel, he talked very briefly about vibrations. In fact, you need to take into account vibrations. And he mentioned some deflection requirements, which I don't necessarily agree with, but I wanted to highlight some of the things. There's a whole design guide when you're talking about vibrations in steel design, and Design Guide 11, and it's a huge book, okay, that outlines the requirements for designing buildings for vibrations, okay? And so modeling for that becomes very critical, okay, like monumental stairs. Morris Merrily had a fuck up when we designed the College of Business building. And if you've ever been in that building, Jake Jab's Hall down there, okay, walk in there because it's cool. Because I mean, there's a big kind of open atrium area, and there's a big monumental stair that was supposed to goes from one floor to the next floor through this big opening, and it has a landing at halfway, and it was supposed to free span from top of stair to bottom of stair. And when it was built, you got a few people out on that landing, and you started jumping, and the thing started resonating. So what ended up happening now, if you go out there at the landing level, there is a support that hangs it off of the floor level above, that mid-floor level, because the natural frequency was too low and you could excite it. So you don't want that in the real world, okay? That was kind of a bruised eye on our case, right? Because and then we went back to the model, and it ended up being a modeling thing. We modeled it wrong, okay? And so we miscalculated what the natural frequency was, okay? And so modeling that. So I wanted to talk about that. I want to talk a little bit about diaphragms and just kind of make some notes about dividing it up over collector lines and areas in which you're going to see forces coming and going through a diaphragm. Also talk a little bit about like doing modal analysis and how you want to kind of simplify the mass distribution so that you can actually run the model. If everything has self-weight, then obviously you're going to have like a million of these different frequencies over which the building is going to vibrate. And it might just be like at 128.3 hertz. You have some beam in some corner of the building that just resonates, right? And that's not necessarily going to be contributing to the overall building behavior. So I was going to make some notes on that. Shear wall is going to make some notes about that, like stiffness determinations. And then I was going to make a couple comments about like brace frames and moment frames when you actually design them. Like when you go in VA and you go to the actual design tab for the braces, it showed you a picture in homework 7, where I showed you like a brace outline, okay, like what a brace frame looks like, and it's got this big, we looked at that was junk. Let's try this one. So we got this beam column intersection. The reason why they do this is that has to be a hinge, right? If you ever see a brace frame where the gusset plate looks something like this, it's 9 times out of 10 a special brace frame, okay? When we were touring the health center across the way, none of them looked like this. They all did this, right? And that does not allow for a nice brace, like rotational hinge of that gusset plate, okay? So they've changed the detailing requirements in order to get that, where this is, 2T, 2 times the thickness of the plate and all this other weird shit. So you got this going on, right? Well, our model is modeling this brace as centerline to centerline of the beam column intersection, right? Well, when you go to design these braces, if you did this centerline to centerline, you're going to have an unbraced length that's quite a bit longer than the actual unbraced length of our brace, right? So just to consider some of those things when you're designing, because when you're designing special brace frames or moment frames, you have a fuse, right? That piece of the puzzle that's going to be just getting destroyed in an earthquake, where all the energy is coming out of it. Okay, so it's critical that you design this appropriately. So I'm just going to make some comments and some notes. So what does that mean? Well, that means I'm going to put some notes together, post it on D2L, and I'll probably just record a quick lecture because I can go a lot faster when you guys aren't here. And I'll just go through those notes and I'll post them. Seem valuable? Seem fair?
If you want to post maybe like more notes, you want to post just like no lectures, post it all.
Okay.
It'd be up to have it.
Yeah. I was just gonna. I'm just gonna cruise through just a few more of these kind of things. I mean, there's a few more on here, but yeah, maybe next time I teach this, hopefully, if I get asked back. With that, right, there's a course evaluation link out on D2L. Okay? So if you don't want me here next year, okay, feel free to speak your piece out there. Craig does look at those as a non-tenure track faculty member who is not Mike Berry and doesn't have a guaranteed place here for life, okay? They matter. They matter a lot more. Okay? So feel free to yell, scream, okay? It's anonymous. I don't get to see it until after the semester, right? You guys know the drill. But honestly, do be honest with what you guys have to say and how you might think this class could be better. I would appreciate it. Okay. So we were on TMS, right, or the Masonry Code. And as I mentioned, a couple of the big things with this code is the fact that they say that you have to incorporate intersecting walls. So a lot of times when you're using masonry, you're using it as a lateral system for shear walls. Okay? The Bobcat Athletic Complex has a bunch of these masonry shear walls in it. I don't know if the health center, if Sam said that they have some masonry walls in there. There were some existing masonry walls in there that were shear wall elements, okay? And you have to incorporate the fact that you get some composite action when you have these walls intersecting at corners. Stiffness, right? Well, this is where we have a conflict, okay, between codes, which happens a lot, right? And I talked to you about how the fact that the IBC is kind of the mother of codes, right? And you can start there, and that code dictates and can actually provide some changes to all of these subsequent codes, material codes. And so you kind of want to go back there and make sure that they don't make any changes that's going to affect your analysis. Well, one of these things that TMS does that ASCE 7 says you shouldn't do is they say, well, you can calculate the stiffness based on the uncracked section, okay? And you might consider when or when you might not want to have that cracked, right? If it's a shear wall, obviously it's going through cyclic behavior. It's going to be like you want ductile behavior, which means you want a lot of crushing and cracking of the masonry. You want yielding of the reinforcement. So for them to tell you that you don't have to do cracked section modulus is crazy in that regard, in my opinion. Okay, but just something to think about. Wood, well, there's some general discussion. It's very, very limited. Wood is dull. Okay, wood is dull. Okay, terrible material. Right? It's got like cracks and splits, and it's not consistent. Okay, doesn't get built in the factory. It's just Mother Nature just gets to do whatever it wants. Okay, so we put a bunch of factors of safety on it. So it doesn't have a whole lot of discussion. ACI, on the other hand, they have an entire chapter dedicated to structural analysis. And there's a couple things in concrete that we need to be thinking about when we're modeling, is the fact that, one, it cracks, and they tell you need to consider the cracked section properties for the material. Okay, always cracks. And then the second is creep, right? You guys have all seen the edges of Cobley Hall, right? The corners that are creeping down. Go out and turn around and you look back. Two corners that are cantilevered or falling. If you go up in isn't your office in the transportation lab? Yeah, like they have those big angles on the floor.
Yeah.
That was in an effort to try and minimize the droop of the corners, right? And they also re-bricked those corners because they were starting to come apart. Like they've deflected that much, right? If you go in the structures lab and you look above the freezer in the structures lab, that whole slab does this. There's a big gap right underneath where my office is. Right, it's just going like this. It's separating the masonry wall. It's got a big crack in it. It's working. I mean, it starts out large at the bottom, gets skinnier as it goes to the top. It's a terrible property of concrete. We do a lot of things to mitigate it. One of the things that we do on the design side is add in steel. Right? It's like, oh, this is a shitty material. What do? We use best material on earth, steel, to mitigate it, okay? So you throw more steel in it as compression steel, okay? The other thing we do is we have to consider reduced stiffness because of creep, okay? So that affects our modeling, right? And they talk about that a lot. Okay, this is a section out of chapter 6, which talks about acceptability of the finite element analysis. Okay, I've got to give ACI a little bit of credit because they're very specific in their discussion about this. One of the big things that I thought was really cool, okay, I think is really cool, is they're so specific, is that they highlight, right, the finite element model shall be appropriate for its intended purpose. They also talk about the licensed design professional should ensure that an appropriate analysis model is used for the particular problem of interest. Right? So what does that mean for you as an EI? I guess it doesn't matter for you, right? Whoever's stamping this has to give a shit, okay? They have to know. So hopefully your model description is appropriate. Hopefully your PM or whoever you're working under, your design engineer who's stamping this project, they'd spend a little bit of time reviewing your calculations, whether it's with you directly or separate from that, right? And that's why I don't know if in your calc sheets you always see like done by, approved by, or checked by, right? When I started working, like the first probably 5 or 6 projects I worked on, every single one of my calc sheets had the engineer's initials on it. We went through every sheet, initial. It was really shitty. Like the first one I got back, it was like a binder that's like, this tall. I think it was Murdoch's actually, up in like Columbia Falls. Okay, so I run through all this shit. He steps in, sets the binder down, and there's probably like 50 post-it notes throughout the entire thing of shit that he was worried about or wondering about or wanted to confirm things. Okay, so that happens. So hopefully they're reviewing that model description and they feel comfortable about it because ACI is telling us that the licensed design professional needs to be comfortable with it. Shall confirm. It's all over the place, right? The licensed design professional shall confirm the results are appropriate for the purposes of analysis. This one's really interesting. The cross-sectional dimensions of each member used in an analysis shall be within 10% of the specified member dimensions in construction documents. So there's even like a little bit of leeway here in concrete saying that you can analyze it and then all of a sudden in the construction documents, you go actually to draw it up, you could make it 10% bigger, which is crazy. Or smaller, yeah, totally. Right? So, it's like a 20 by 20 section, all of a sudden it could be like a 19 by 19, right? It's just like crazy. Crazy. So that's concrete for you.
Do you write a model description for every model that you make?
No, not necessarily. There's very
Yeah.
Hey, this is not for me, okay? All right, I was being honest. I could have totally lied to you, but I'm not. All right.
So we're cutting that from all.
In academia, do I do a model description for every model I do? Yes. In the real world,
But in the real life.
not as often.
But when you do
Like larger projects that are definitely that I know like that were on MSU's campus or in the city of Bozeman, I would write up something. And obviously you guys now have experience doing them, right? They don't take that much time. You're just trying to spell out to some level to give somebody an idea of what you did, right? But in general, when you start going through like modeling frequently and often enough, people have a general sense of what boundary conditions you're going to put on something, right? If it's a very simple like moment frame 2D analysis where you just like draw 2 columns and have say 2 beams at 2 levels and you apply some loads, they can more or less kind of get through that model and dissect it themselves in probably 5-10 minutes versus giving a model description, versus like NAH where now they have like 2 different folders and there's 3 different models and one model combines things, another model is just gravity and another model is just lateral, right? It affords itself to have some sort of description.
Forwards. Is that a word? That's a good word.
That's a word. That's a word. Jesus. It's so critical. I feel like I'm like under a magnifying glass.
I like it.
Appreciate
Sounds good.
Good. It's not very large. It's not very big. I worked in the construction industry. F word is in there way too many times. If you guys haven't noticed already.
Yeah,
I say it in 208, and I'm like, oh man, I probably shouldn't have said it, you know. And then it's recorded, and then it's on YouTube. Like everything I say, I'm like shit. And then, you know, if I give it out, then they're like, yeah, you know, Tim has got a pretty foul mouth. I'm like, no, I don't. Here he is. You know. So anyway, don't tell on me. I want to be here next semester. Okay. Maybe some of you don't. Those of you that are going to be here next semester. Concrete, 400 level concrete. Yeah, stoked. Right?
You better pick up that lab manager role.
Oh yeah, then I can be around here all the time.
Yeah.
I don't know. I like where I'm at right now. It's been a nice balance. AISC 360. Okay, steel. Now we're getting into the good shit. Okay, good stuff. All right, chapter B, design requirements. They have an entire chapter over design, right? Talks about design. They have some really cool, nice descriptions of what simple connections mean and the assumptions that we make. You know, simple connections shall have sufficient rotation capacity to accommodate the required rotation determined by the analysis of the structure. Okay, what does that mean? Well, if we assume that it's a pin, okay, that's why in the shear tabs chapter of, I didn't bring a 360, but in the shear tabs chapter, when they talk about a shear tab design, that's why they limit the thickness of the shear tab, is so that it can actually yield and rotate, and it gives some rotation capacity, so that we can assume that it has, acts as a pin, right? It transmits a negligible moment. Okay? When we get to moment connections, there's some really interesting ones. I don't know in steel design if Damon talked about partially restrained or fully restrained, right? FR moment connections versus PR, partially restrained moment connections. Okay? If you don't do fully restrained, that's essentially saying that you're connecting all the elements sufficiently, that there's enough stiffness there, that it has, what's it say? A FR connection shall have sufficient strength and stiffness to maintain the initial angle between the connected members at the strength limit states. Right? So underneath all of your LRFD load combinations, there's enough stiffness there that those two, if they're connected at a perpendicular angle, that stays at 90 degrees. You go to partially restrained, which there's partially restrained moment connections. I personally have never designed a partially restrained moment connection. You always assume that it's fully restrained, but there might be some conditions where this might make sense, okay? Is where you have, right, the component elements of a PR connection shall have sufficient strength, stiffness, and deformation capacity at the strength limit state. Based on the response characteristics shall be documented. What's this? Okay, the moment connections transfer moments, but the rotation between connected members is not negligible, right? So now if it's connected at a 90-degree angle, that angle might not be 90 degrees once it's pushed on, right? If we had a moment frame and we pushed on it. And so then that rotation, you no longer have on those beam column locations, it's no longer going to be perpendicular when you push on this. And so this might end up being a rotational spring, right? It's going to act as a spring. It's going to have some stiffness based on the rotation of this beam, okay? And that rotation of this beam is going to be a function of how much force is applied. And so it's basically telling you that, hey, you can't just assume that it's fixed. You're going to have to put a spring there, okay? So if you're ever doing partially restrained, just know that you're going to have to model something like this, right? There's some literature attached to, I'm sure there's some research on different connection configuration.
I was going to say, is there research on that? Or
Yeah, there would have to be.
proprietary?
Yeah, if you look at it from a mechanics sense, right? You have this node that has stiffness of column, and beam all framing into one node, right? The ability, if these stay fixed and this rotates, you could figure out what that stiffness would be. It'd be essentially the stiffness of that beam bending, right? So you could come up with some stiffnesses. Rationalize it some way or another.
It's weird, like counting on a pin connection, like the pinness of it coming from failure in like the connection. Like with the shear tab, you're saying to have it small enough so that I can yield.
Oh yeah, that
Essentially-
you're
And essentially fail, which is basically the same thing as this. Like this is just a fit partially restrained, which is the same thing as our pin shear
yeah,
tab.
and I guess not.
Like I don't understand what the difference is. Where we're in both cases, there's it will carry some amount of moment and it will deform. Like,
Yeah, I would
the
say
strength.
I
of
wouldn't
the
say
moment.
necessarily that it failed, Elias, as it has a reduced stiffness. So, like if you had a shear tab, like the connection of this beam to this column, right? It has a shear tab and it has bolts on it, right? The stiffness of this due to rotation, if we looked at it in section view, right? Now we've got these bolts that are going through this, right? If this, the stiffness of this is a function of its thickness, right? VH cubed over 12 sort of thing, right? And so what they're telling you is they limit the thickness of this. So they're saying at some point, right, when that thickness gets so big that when this beam does get loaded, it acts as this torsional spring. And they just want that torsional spring to be weak enough that as it makes it through its rotation, that it's not going to transfer a whole lot of moment. It's negligible, right? They know there's going to be moment transferred, but it's going to be small because we reduce the stiffness of this like connection piece. Whether it's for a shear tab, it's a plate, right? And they limit your thickness of the plate. For a like double angle, sometimes they'll put, right? We'll weld an angle. So now if you looked at this, just draw it right here.
Would you ever want to model it as a fixed connection and make sure there's not very much moment going into it, like to where if there is a lot of, like if it were a fixed connection, then there would be a lot of moment dumping into that in your modeling as pin, but really it's like a little bit restrained, like you're just gonna rip that shear tab is kind of how I'm seeing it, like when there's actually no ability for it to rotate other than the failure of the shear tab is the only thing that allows it, like deformation of the shear tab. And then maybe little deformations, I guess you'd have to know how.
I would say if you went outside the box with respect to like connection design and configuration. So in 360, I don't know if in steel, if Damon had talked about like, there's a whole section in the steel manual at the beginning portion that's all about simple shear connections. It's a tab called shear. And it walks through like all of these different types of connections. Double angle connection, they have stiffened seat connections, they have shear tab connections, they have extended shear tab connections, they have all these different connection types. And in each of those connection types, they talk to you and tell you, say, hey, you need to consider the moment, and you need to consider the moment of, like, on this bolt group, because you're saying that, like, in some of the connections, they're designed and there's limits, like there is for the thickness of your shear tab, okay? All of those kind of pre-configured connections have had that kind of analysis that you're talking about already done to them.
So researchers have
Yes,
already
they
figured
research
this out
them,
for
they've
us.
come up with different
So
configurations.
trust that
They tell you
AISC
that,
is
oh,
that-
hey, all of a sudden, if you got another row of bolts, now you need to consider the moment on the bolt group. Whereas if you have a single row of bolts, you don't have to do that. If you have an angle that's connected to a column, right, they tell you that, hey, you can weld the side and the bottom, but you can't weld the top. Like all of those things. Like if you looked at this in you know, elevation, or sorry, like looking at it from this direction, and these are your bolt holes, right? They tell you, well, you have to do this is 2 times the size of the weld, return on the top, but then you weld the side and the bottom. And the reason why you do the return is so that when this does rotate and flex, they don't want you to rip that off, right? A crack to start at that corner and just rip this connection off the thing. So they've thought it through, right? Yeah, they've gone through a lot of
To add.
testing, yep. And so then they tell you based on the configuration what you need to do. So if you went outside the realm of all of these connections and you were going for whatever you wanted based on the configuration, you just have to think about it from a mechanics sense. And maybe, yes, you would say, I'm gonna design it as stiff, right, or fixed, and I'm not gonna allow it to rotate. And then your model is going to adjust for that, and the loads that you get out of your model is gonna assume that it's fixed, and then you're gonna design that connection for fixed, right? So you just have to think those.
The really big moment applied to that would cause failure in that shear tab, even if you're counting on it not to transfer any moment, right? Like-
For sure, yeah, but that's why in those configurations, they limit you on the thickness of the shear tab. They limit you on the rows of bolts that you can provide, right? And then they say, okay, if you have more than 2 rows of bolts, you gotta go to an extended version. If you do an extended version, then all of a sudden you're designing this plate for some moment.
I remember in Structures 1, like the first time Audrey drew a simple connected beam and just drew like shear tabs, and I'm like, well, that's not pin at all.
Yeah. Well, as
"No,
you
that
know,
is pin," and I was like, what? I was so confused.
as you know, we make huge assumptions as engineers, right? When we're analyzing these things, we go from Roberts Hall to this little
Pins.
pins and fixed and make an assumption on the members. ACI goes and tells you can have 10% difference in your cross-sectional dimensions, right? which is really interesting. I just caught that one because if you were analyzing an existing structure, you could essentially go in there and beef up everything by 10%,
That's ridiculous.
right? When you're like,
It's such a way to cheat.
yeah, totally.
It's like, no, it's
If you wanted to, you'd have to be comfortable doing it. But yeah.
Yeah.
So those are connections, okay? If we talk about in the appendix, well, the appendix says, hey, right, it's really, and this is in 360 still, right? So in the appendix, they said designed by advanced analysis. What do they say? Well, they're opening the doors to allowing you to use the power of the finite element analysis method and saying, hey, we know we have really capable computers, really strong analysis software programs. If you really want to sharpen the pencil, and in some cases, like there's, when you do a big high rise and they do experimental designs, like there were some big ones it was on the western seaboard where they started doing this composite construction with concrete and steel, where they essentially used the steel as the formwork and then had a bunch of headed anchor studs in it, and then you cast concrete, and that's the concrete core. Well, there was no like predetermined lateral system, right? That was prescribed, that had an R value. So then they're saying, hey, if you want to spend the time and do use of a more advanced methods of structural analysis to directly model system and member imperfections and or allow for the redistribution of member and connection forces, right? Plastic design, you guys are dealing with that. And moments as a result of localized yielding, you can do that, right? Designed by and you can do it on an elastic analysis sense, which is what we've been doing, or you can do a inelastic analysis, right? Where you start letting things yield, and then that affects the fact that, okay, when it gets to a certain strain, it's not going to continue to increase in strength, right? Resistance and stress. It's going to say cap at 50 KSI, right? Or this analysis, you might want to consider the fact that everyone has seen a stress strain curve for steel, right? It goes through and then it strain hardens, right? It actually gets stronger, right? So you might want to incorporate that.
These connections, right? Like that it's within that like elastic region.
Well, yeah, I mean,
Deformation. I would imagine.
yes, I would say that they're more worried about relative stiffness is the important part about these connections, right? And that's why with partially restrained moment connections, you have this torsional spring, right? So it's like, where does your connection land? Is it going to be completely fixed and not allow much rotation, right? It's going to be really stiff, or is it going to be flexible enough that we can negate it, right? We're going to say that our member displacements are going to be small because we typically maintain that they're pretty small, right? We don't want to see them with the naked eye. And so it's not going to go through a whole lot of rotation, but all we want to know is that in that small amount of rotation, how stiff is that connection? So, but you can directly model that if you knew what that was. They're saying, hey, doors are open, go for it. All right, and the hope here, right, is that we're pushing our mathematical model closer and closer to the real world, right? That is the desire. Because as we get closer and closer, then we feel better and better about that we're actually modeling it. We're making less simplifications, which generally amount to conservatism, which amount to larger structures, which amount to more money, right? We can save money by doing a more in-depth analysis. Then we get to AISC 341. Have you guys opened that book yet in class? You never got to it? Did you get to like special brace frames or moment frame design?
We did special concentric brace frames that you talked about, but we never actually had to open it.
Wow. Fuck.
Because you always just had stuff.
You just had stuff? Okay, this is a like crazy book, okay? There's a lot of shit in this thing, right? It's about the thickness of the steel manual, right? And for us who are lucky enough, those of you who are lucky enough to stay in the Rocky Mountain regions, we really do have high seismic, okay? You get people from California, you'll see when you ever go to conferences and stuff, it's like, if you're from anywhere else other than California, it's like, you're really, okay? You're like, oh my God, you don't have to deal with seismic, but once you tell them, hey, we're next to the world's largest volcano, okay, we deal with some of the largest, seismic design categories, D and above, okay? We have to deal with this thing, okay? All right, otherwise, down in Colorado, not so much, okay? Not so much. You might not have to deal with it as much. Okay. Even if you go as far as, not as far, you're going to like Billings. Billings has seismic design category B, right? It's like you're cheating when you get out there. Okay. And there's some engineers that never deal with this ever, right? They never have to deal with high seismic, okay? So we are very lucky, and we live in a place where you got to deal with this book, okay? And you got to start designing towards it. And they have a lot of discussion on modeling because, as we know, most of you know, okay, most of you have taken, or some of you have taken Mike's seismic, like dynamics course, right? Stiffness is a huge contributor in how forces are distributed in a building.
Is that your book?
This is, yeah, one of them. I've got 2 of
I
these.
was gonna say, why isn't it tabbed out?
I want to own this tab a little bit more. I got out of the game right when this, got out of the game. I left Morrison Merrily when this just started and I was project managing and I didn't open these books very often, okay? If you go to the maroon ones, which are before this, they're destroyed, okay? That's where my that's where my street creds are at, okay, is in those books, okay? Cover's missing, it's tabbed up all like crazy. I'll bring that shit in, okay, and then I'll show you. I'll bring my books in, all right? That'll bring me back. You guys will believe me a little bit more, okay? This is too clean for you, huh? Damn, just lost it. I shouldn't have brought this in. I should have brought another one. I had it all semester, and then all of a sudden I lost it, okay? Well, they have a lot of discussion in the maroon one and in this one, okay? They even have more in this one because this got a little bit thicker. They all seem to just get thicker and thicker, okay? Keep adding shit, all right? They have a analysis part in this. That's what this is. They have all sorts of discussion about analysis procedures, where they're doing elastic, inelastic, plastic, because steel is so cool, right? It's just like all the properties are so known, right? It's Amanda believes this, right? Amanda wrote a paper on how amazing steel is. You guys know this?
No.
Okay, I'm gonna dig it up. I'm gonna go find it. It's got to be published out there somewhere.
It's not published.
It's got to be.
Only AISC has it. It was for my scholarship.
I know, but wouldn't they like say, hey, like this is the winner? I'm gonna. Well, you should send it to me so that I can share it with the
Okay,
class.
this is the second time he says awesome.
You should
I
send
hope
it.
you forgot.
No, hell no, hell no. Steel's my jam. Steel's my jam. Okay, you want to get on my good side? You start talking about steel, right? Elastic, inelastic. You can do plastic. Everything follows mechanics so beautifully. Okay, and all these stability design stuff. I know you guys worked in Damon's class about like stability stuff, right? Effective length factors, all of that. Direct analysis method. Okay, they talk about all of this and how it works and how the big part of this code, right, is seismic. So we talked about this equivalent lateral force procedure, which some of you guys will learn about in the future, but we talked about it briefly about how we divide up this seismic load throughout all of our levels based on the mass, and how you do that with the direct analysis method, because they say, hey, well now we're pushing on our building. This building's gonna have axial forces, so we push on it. Well, that's going to really exacerbate our P delta effects, right? We're gonna have all of these axial loads, they're gonna be deflected over, so we're gonna have P delta, we gotta deal with that. We can deal with it the direct analysis method. Modal response spectrum analysis, right? Modal analysis, well then, in that case, same thing. We start looking at the modes of vibration of our building. Then they talk about, this is probably the nuts and bolts of it, talking about the stiffness of structural elements, the strength of structural elements, base plates, foundations, diaphragms, that's the most important part, right? So it outlines in here, it talks about P delta analysis, and it's so specific, it's so cool, because it actually outlines saying that, hey, some modeling softwares, they use an iterative approach, right? A lot of them use a non-iterative approach. What is VA doing? Non-iterative, right? They even go as far as explaining about the geometric stiffness matrix in here, okay? It's real, right? It's so cool, okay? It's real. I'm not just teaching you shit. I got street credit, all right? I'm bringing in my codes. Structural modeling, okay? They talk about element stiffnesses, whether it's steel, if it's composite with concrete. There's some lateral systems that allow you to, say, take a wide flange steel column, you weld a bunch of steel rivets to the side of it, and essentially encase it in concrete, and then you get this overall, like, composite member, right? They talk about connections in panel zones. If you remember in ASCE 7, I feel like I'm talking faster because I'm getting excited, okay? In ASCE 7, they talk about all this, right? Stiffness properties of concrete and masonry, but on top of that, they say, for steel moment frame systems, the contribution of panel zone deformations to overall story drift shall be included, okay? Well, they talk about how you can do that in AISC 341. And they say, hey, by the way, if you run a model, right, this is our brace frame model, where we have columns and beams. Our columns and beams run center line to center line, right? Well, in AISC 341, I'm not gonna, oh, we got lots of time. I think just cruising right on, aren't I? It's getting out the high-tech shit here.
Some homework questions.
You have homework questions? All right, look at that. Modeling end offset at panel zones. They say, hey, by the way, right, the code says you need to account for the fact that this is going to have different stiffness. You got maybe some stiffeners that run between your flanges of your column, okay? And you need to take into account that when you're looking at your analytical beam and your analytical column, right? These are your elements in your finite element analysis. Well, what is the long story short? What do they say? Well, hey, by the way, if you do a center line to center line approach, you're gonna pretty well model that behavior, the panel zone. Pretty sick, right? You don't have to do all this crazy shit that you might have thought if you did, okay? But they do talk about the fact that you can change that performance and behavior, right, with these connections and the panel zone stuff. It's worth a read, right, to read through this. If you're ever modeling a seismic lateral force resisting system, okay, and you're going to devise a model, read this section, right? Read about structural modeling, okay, when it comes to steel, okay? They have a lot of things to say, right?
2.4 in the seismic design.
2.4 in the seismic design manual, right? When they talk about stiffness of structural elements, they have a huge conversation about this idea with steel beams with composite slabs. And the fact that if you're modeling it, you've got all these headed anchor studs sitting on top of your beam that connect your, right? Have you guys done design of composite members?
Yeah.
Okay, good. Man, almost lost all faith. Right, so you got this steel beam, got this headed anchor stud, and all of a sudden you got this, oh, that was nice. Do this. Okay, got this metal deck that's sitting on here. Right, then you got this concrete sitting on top of it. Well, when you're in positive bending, this is in compression, that's gonna stay together, right? You're gonna have some nice stiffness associated with that. If it's a negative bending though, right, all of a sudden this thing becomes in tension, starts cracking apart, it's not really gonna do anything for you, right? You might just have the stiffness of the steel beam. So if you have this model that's a moment frame, so this is a moment frame beam, you have reverse curvature in this beam as you're pushing on this building, right? You're gonna have stiffness that's added based on the fact that you have parts of this beam that are in positive bending and you got this in concrete and compression. And then you have areas where it's not contributing, right? How the fuck do you model that? Well, you look down here and you start reading about it, and they say, oh, hey, by the way, you're gonna have the modulus of elasticity of the steel plus the the moment of inertia of the steel member in negative, plus you're gonna have the modulus of elasticity of steel plus this I lower bound. Everyone remember what the I lower bound was?
Yeah, it's been a minute.
Okay, it's the lower bound stiffness associated with having the shear flow attachment of your stud, right? Each one of these had a Q, right? It was your shear flow, like how much stud strength you have per stud. And that allows you to transfer the shear flow, which then allows you to have an axial force in this, which gives you moment, right? Shear flow gives you moment. Shear flow comes from a change in moment. And so this I lower bound, which there's tables in the 360 manual. And so they say, okay, you can come up with an effective EI, right? And then all of a sudden now you have this effective EI if you were going to consider your the stiffness of your composite section in your model, and then you need to do something with that in your model, right? You need to affect your elements of your model based on that, okay? And they give you abilities to do that. Panel zone. This one is cool, okay? This is diaphragms for three-dimensional analysis, okay? What are they saying here? Well, they say all sorts of cool shit about the stiffness of it, how you model it, the negatives associated with it being a rigid diaphragm, right? A rigid diaphragm model prevents relative in-plane movement between nodes on a given floor. Any ideas why that could be bad? If you have a diaphragm, right, say it was the second floor of Roberts Hall, okay? You have all these lateral system extending through the height of the building. They might offset between floor levels, okay? And then all of a sudden you say, okay, code allows me to make this diaphragm rigid. Rigid means that this diaphragm has dimensions, it doesn't change, right? It's infinitely stiff. You push on it, it's not deflecting. It's not gonna act as a beam. It's not gonna, crack or rotate in the plane of the diaphragm, okay? Any bad things associated with that? Still think so.
You're talking about preventing in-plane movement or like this complete stiffness?
Yeah, so axial forces will not develop in horizontal members connected to the diaphragm. Okay? Well, we have drags, we have chords, we have collectors that all need to be designed for axial forces, right? Well, if we're assuming this diaphragm stays the same dimensions, we're going to be holding all of the members that are in that diaphragm to those dimensions. You're no longer going to be able to strain them. You're no longer going to get axial forces out of them. Where a lot of times we have axial forces, right? Based on dragging load into something or dragging load out of something, okay? As I mentioned, when you do this semi-rigid approach then, let's go back to here, I guess. Right, we kind of have these three assumed kind of behaviors that we can look at in diagrams, okay? We've got the Aaron, flexible, right? And then we've got the rigid, right? And then semi-rigid, that's where I'm at, okay? I said Aaron because they always deal with wood, which they assume is flexible, right? And you just do a tributary width, copped out, right? So we got rigid, semi-rigid, and flexible, right? And so if we do rigid, we get no axial loads in our cores and collectors, which could be a problem. We might just go in the model, someone says, you say, hey, Jim, design these axial members, okay, or these cores and collectors, and then they go in the model and nothing has axial load. They're like, oh shit, we're good, no axial load, done deal, model it, right? When in reality it does. So then that's where the code kind of has some description of, well, there's a trade-off, right? You get some simplification based on assuming this rigid behavior, which we can assume based on the code, but it's going to affect how this thing really behaves, right? And they give some comments on the fact that, hey, the semi-rigid might just be the best approach because we have the tools to do it, okay, as long as it doesn't become too cumbersome. We're really trying to figure out what that stiffness is, okay? And so we can model it, right? And we might want to model. But when you do semi-rigid, then you have to really put some thought into the stiffness of that diaphragm. And that's when they start talking about how, let's see if we go back here. Right? Diaphragm slabs can be modeled using either membrane or shell elements, right? We're familiar with that shit. In-plane stiffness reduction factors should be applied to account for cracking of the concrete and other factors that decrease the membrane stiffness of the diaphragm. Membranes differ from shells in that membranes do not provide out-of-plane rotations of stiffnesses, which can increase the computation of the band, blah, 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 right? So, I mean, this is beautiful. They give you really nice kind of guidance on how you model these things and what you should be thinking about, right? They're kind of giving you guardrails, if you will, right? Because in the end, there's not I feel like when I went to school, like the first 3.5, maybe even almost 4 years, I felt like it's like, oh shit, I'm going to sit down. There's a right answer, right? I'm going to sit down, I'm going to get all my pieces together, and I'm just going to design it, and it's a done deal, right? And it's the right answer. It's like, that is not even close, right? There's a million right answers, and it all comes from the fact that we make so many assumptions when we come from Roberts Hall down to analyzing the spandrel beam that's above these windows right here, right? So there's a million different answers, and you just have to think about it, and the code is there to kind of put these guardrails on there so that they are saying, hey, you shall be thinking about this, okay? You shall do this, or you should do this, right? There's both of those. There's things that can be interpreted a million different ways. And so they give us some guidance as to how to do that, and how to implement it is going to be up to you guys, right? And so you might decide to have areas pure rigid and others semi-rigid. Maybe there's areas in your diaphragm that don't necessarily are not affected as much with respect to that kind of loss of axial loads, okay? But it does reduce the computation, right? You just have this fixed. VA, you used to be able to just pick a floor level, pick nodes, and click a box that said rigid diaphragm, and it just fixed all of those nodes relative to each other in that kind of geometry. Okay? They got rid of it because I think Adam agrees with me in saying if you're gonna model it, just model it, right? Make it semi-rigid. But I'm sure in other platforms like RAM, can you just select? You guys have you done something? Yeah. Okay, well, we're gonna ask John on Wednesday, right? What RAM does with respect to rigid diaphragm. Sutton, you're our in-house expert. Lisa,
Yeah, you can do rigid, flexible or something.
and so you just like you take a diaphragm and then attach a performance of that rigid diaphragm. You just say
Yeah.
like it's rigid, it's semi-rigid, or it's flexible.
Yeah, and if you assign it as rigid, I've always been able to do handhelds.
Yeah. Well, yeah. So like, agree. Like your decision on using one of these three.
Like if you have a basic square building, the rigid,
Yeah.
that's pretty good. So
Or-
I've never
yeah.
played around with semi-rigid because I've never done anything.
Yeah.
I know you can.
Okay.
It's all for you.
Okay. Yeah, that's cool. That's neat. So you might decide to have a hybrid of having these rigid and semi-rigid. Okay. You can also say decouple this 3D structure into 2D frames, right? Line and point loads. They talk about it in this analysis, saying, hey, if you do have a rigid you don't need to find an element program to analyze a rigid diaphragm. Okay. If you guys were you probably learned in concrete. You guys in concrete and talked about rigid, and you have torsional displacements and translational, right? And how those affect the forces in your lateral elements, right? You can do that as a 2D analysis at the diaphragm level, and then take those forces and dump them into, say, a frame, right? Our two level frame I have here up on the board. Okay. Damn.
This is our last class.
This is our last class. So Wednesday, right? Wednesday, John Lovren's going to be here from DCI, okay, unless he cancels in the next 2 days. And then Friday, Adam Stordahl's going to be here again from IES. He's got another example we're going to go through, okay? He's going to teach you never, if you have a firm, if you work for a firm that's uses VA, right? You're going to be just deathly scared of sending him the emails, right? This is probably a good thing, okay? All right. I really want to see this wall that they have of like the people, right? The astronauts and like shit. I might be on that wall. I might be.
Decided when our exam goes.
No. I am going to give it. So then Adam's going to be here. There's no class in here on Friday, right? So we're going to have a nice conversation with Adam, and then at some point, okay, he's going to have to kind of shut it down at some point. But there's no class in after this class, so I'm going to hand the final out after that class. And I'll just walk through it after Adam's done, and then you guys can take it on your way.
Do Wednesday when we start our
I haven't
tour.
decided yet.
I think that'd be like, and it's the last time we for sure see you, like you can beforehand.
It depends on how nice I am.
You seem like.
I mean, I felt pretty nice until you guys were ridiculing me about the lack of tabs in my book, okay? That really hurt my feelings. All right?
It's just
Yeah, so then we're gonna have a tour of the field house next Wednesday at 3 o'clock in the afternoon, okay? And I feel like you can get out of your tutoring shit, okay? What'd she say?
I was defending the accent.
Yeah.
Well, I just knew what I meant. So I can't get out of it,
But you'll have it done before this.
So hopefully
And then you can
the
party.
test isn't too long, so I don't have to try and finish it between 11 and 3 on Wednesday.
Dawson, you're always finishing shit half the time everyone else says. So you can-
I come.